And while these elements can be combined into networks of ever-increasing complexity, they always obey the same simple rules, called Kirchhoff's Laws. Gustav Kirchhoff, a German physicist, was keen on mathematics. By applying Ohm's law and generalizing it fully, he derived two laws, and each expresses a familiar idea. One of those ideas is conservation of charge. And the corresponding law for circuits is, whenever one current splits into two, or vice versa, the total current into the junction will equal the total current out of it. Kirchhoff's other law expresses conservation of energy. An electric charge going around any complete circuit neither gains nor loses energy. Consider an electric charge in space, not confined to a circuit. If it's moved through space on a path that brings it back to its starting point, no net work is done. The electric potential, or voltage, may go up or down, but it always gets back to where it started, and the same is true inside the circuit. Notice that an integral along a closed path has a special notation, an integral sign with a circle on it. So, in the special case of an electric circuit, all the voltage rises due to batteries and charged capacitors, and all the voltage drops due to currents flowing through resistors add up to zero. Using these two laws alone, engineers analyze the most complex circuits.
All right, so this is what he's talking about, Kirchhoff's rules. All right, so you got the junction rule based on the conservation of charge. The amount of current going into the junction and coming out of it should add up to zero. If it's going into the junction, so we take that to the positive. If it's leaving the junction, we take that to the negative. So this is the junction rule, or the Kirchhoff's current rule. Just remember the initials per se for the multiple choice section of the test. The second one is the loop rule, Kirchhoff's voltage rule. This is based on the conservation of energy. So the total voltage drop and the total voltage gain is going to add up to zero. That's what it means. Okay, so once again, the basic rules regarding the current and the resistance. If the loop and the current, if they're in the same direction, there's going to be a voltage drop across the resistor. If the current and the loop in opposite directions, there's going to be a voltage gain across the resistor. If the loop is going across the battery, if it goes from high voltage towards the low voltage, it implies a voltage drop. If the loop is moving from low voltage towards the high voltage, remember it's just pointing this way, there's going to be a voltage gain. That's it. All right, so this is the stuff that we covered last time as well as this. All right, so the question is what happens when you go across a capacitor? So that's the stuff that we are interested in. Okay, guys, so this is the stuff that we will cover today, and that's it. Okay, so the current is charging up the capacitor. That's what it means. So current is coming in, it's just charging up the capacitor. Your capacitor is in this direction. If the current and the loop there in the same direction, this is going to denote a voltage drop. So this is going to be negative. If the current and the loop, if they're in opposite directions, this is going to denote a voltage gain. Once again, so these are the rules that we will get to use. Current and the loop in the same direction, voltage drop across the capacitor. And if they're in opposite directions, it's going to represent the voltage gain across the capacitor. All right, so against that, quick background. All right, let's set up our observations. 20 amps of current. It's how much current is pumped into the chest cavity. Somebody's having a heart attack for 1,000th of a second. So what's the idea behind it? It takes an amp of current to stop the heart. And if you can just stop the heart for a fraction of a second, it's an electrical device. It's going to reset itself. So you have to stop the heart only 1,000th of a second. So the duration is important. You need to be able to send 20 amps of current. You need to be able to pump 20 amps of current into the chest cavity within only 2,000th of a second, no more than that. So it's mini lightning, except this is highly controlled. So how do you control the duration of this charge? Once again, we have the same problem here. This is flash photography. Notice that they're able to take the picture of a bullet as it's just going through a banana. All right, and then the flash illuminates the scene within 3.3 tenths of a millionth of a second. All right, so once again, how do you control the discharge time? How does the magic happen? All right, these are known as RC circuits. Obviously, the capacitor is what you get to use. You will charge up the capacitor. You will also discharge the capacitor. So how do you control the charging and the discharging, the charge up time and the discharge time? All right, the time it takes for it to charge up and time it takes for it to discharge. You can control it two ways. Number one, the capacitance is going to give you how much current that how much charge you can place within the capacitor. Resistance is the stuff that you need to use in order to control the charge up as well as the discharge time. All right, so here's your battery, and here's your switch. You can turn the switch on, which means that it's going to charge up, or you can just turn off the switch, which means that you can discharge it using that. All right, so this represents the charge up. This is the amount of time it's going to take for it to charge up. All right, so notice that there's a gradual process of charging it up, and you're charging it up to its maximum value. All right, so you turn the switch on, it's going to gradually charge up. All right, when I say gradually charge up, it's expressed in terms of milliseconds. So this is 1,000th of a second. All right, so it's not instantaneous, it takes time. That's what it means. How fast you're going to charge it up depends on your capacitance value, it depends on your resistance. And then you turn the switch off, and then what's going to happen is now it's going to discharge. Notice that the discharge is an exponential process. There's an exponential decay. So mathematically, this one is straightforward. And mathematically, this one is slightly more complicated. This is not an exponential increase, but this is an exponential decay. All right, so how do we come up with mathematical expressions for these? All right, so the mathematical expression that you come up with this is known as a derivation. Okay, so this is an RC circuit, so it's a resistor capacitor circuit. You throw the switch. All right, so you throw the switch here, so which means that this thing is going to charge up. There's going to be current, so this thing is going to charge up, basically. All right, so mathematically, how do you do this? You end up using the Kirchhoff rules. It's a standard way of doing it. So once again, you have to start from, you connect these two. This is going to be your point A. The current is going to be moving in this direction. And then you have to loop. You have to figure out which direction you want to loop this. All right, so I'm going to set up the direction I want to loop. I usually like looping. Let's get out of here. All right, so my preferred direction is usually clockwise direction. So the loop is going to be moving this direction. I'm going to have the current move in the same direction, so I'm going to assign an arbitrary direction for the current. All right, notice that the current and the loop are in the same direction. If the current and the loop are in the same direction, so what's going to happen here? So there's going to be a voltage drop across the capacitor. So how do we indicate the voltage drop? That's going to be Q divided by C, right? So this is going to represent the voltage drop right over here. All right, so the current going across the resistor, there's going to be a voltage drop here. And the current going across the capacitor is also going to experience a voltage drop across the capacitor. And then what happens? Loop is moving in this direction, so there's going to be a voltage gain there. All right, so we write up the Kirchhoff's equation. This is the loop rule. Starting point is going to be right here. Okay, so there's going to be a voltage drop here. All right, so the current going across the resistor is going to experience a voltage drop. Loop and the current there in the same direction, so there's going to be a voltage drop there. And there's going to be a voltage gain whenever you go from a negative terminal to the positive terminal. All right, so you write out the equation, and that's it. All right. And then you have to evaluate the equation and then come up with an expression regarding how the charge fills up. All right, so the current is going to be represented in terms of the net charge per second. All right, so this is in the differential form. And then this turns into a first order differential equation, which is solved using this method. You could use calculus if you wanted to, but I like differential equations. Because differential equations is not required for this class, I'm going to skip the details. The only thing that I'm interested in is the end result. So the differential equation is, and it's going to give you the final equation. So let's just focus on the final equation, the meaning of the final equation. The meaning of the final equation is what we will need to focus on. We got Q naught. What does Q naught represent? Q naught represents the maximum amount of charge that the capacitor can hold. All right, so which means that within this time period, which is T, what's going to happen is the charge gradually is going to build up to its maximum value. All right, this equation that you're looking at represents this curve. All right, so which means that this is the equation that represents the charge up. So which means that this charge is going to gradually build up to its maximum value. All right, one of the things that we need to talk about for those of you guys who want to go to grad school at some point is this expression here. All right, notice that this expression is an exponent. All right, so you know T is going to have the units of seconds, so this is the time. This is your time axis. If that's the case, what does RC represent? What is the unit for RC? Okay, so the resistance times capacitance. What do you think that the proper unit is going to be? Any ideas? Okay, guys, those of you guys who will take the, those of you guys who want to go to grad school, they will require, some schools do require that you take the GRE test. On the GRE test, they usually don't ask me any knowledge-based questions because who's going to remember all these details? No one does usually. All right, but they do ask you questions that require a little bit of thinking. And this is one of those thinking questions, critical thinking questions. All right, so what they would ask you the meaning of the proper unit for RC here. So what do you suppose the proper unit for RC is going to be? All right, so what's the unit for R? R is going to have the units of ohms, and C is going to have the unit of farads. All right, so you got ohms and you got farads. So what is so the question is ohms, farads. You multiply these two, so what do you get? And then rest assured, that's going to be one of the answers. On the multiple choice section of the test, that's going to be one of the answers. I can tell you, it's going to be one of the answers. Okay, Ian, give yourself 2 points. It's going to be one of the answers for sure, except it's not going to be the right answer. All right, so what is the right answer? And okay, so you will remember this when you're taking the test. This is one of the standard questions, those of you guys who will take it. The proper answer is going to be ohms times farads is going to be, I'm just going to pull something out of my ass. I'll pull a Trump. I'll say, for no reason at all, it's going to be seconds. All right, so the question is, what the hell? Okay, so that's the best question I can come up with. Ohms times farads is going to give you seconds. How's that possible? Okay, guys, this is an exponent. What kind of units do you think that the exponents can have? Exponents are unitless. All right, so if this is a second, you know this has to be a second as well, right? All right, so that's the reason why this is going to be seconds. All right, so that's just the weird mathematical detail. Exponents cannot have units. You know time has the units of seconds, so which means that RC has to have the units of seconds. So which means that RC is related to time. That's what it means. Hence the reason why it's known as the capacitive time constant. So the combination of RC acts like a time. It's got the time units. So we use the Greek letter tau. This means capacitive time constant. So what does it represent? Okay, what it represents is something that you find out from books. What it does represent is it represents the amount of time it takes for the capacitor to charge up to 63% of its maximum value. All right, so technically this is what it represents, but conceptually, what does it mean? All right, so when you equate T to tau, to capacitive time constant, it's going to give you 63.63. That means that capacitive time constant, according to the book definition, and I have to give you the book definition because this is what most of your professors will use, and then I'm just going to jump into the real physics of it. Book definition says this is the amount of time it takes for a capacitor to charge up to 63% of its maximum value. Okay, now that we got the book definition out of the way, let's talk about the reality of it. Guys, capacitive time constant tells you how fast you can charge up or discharge a capacitor. That's it. All right, this represents how fast you can charge up or discharge a capacitor. Okay, so now that we are talking about reality as opposed to what the book talks about, notice that the larger the resistance is, the longer it's going to take for it to charge up. Larger the resistance is, longer it's going to take for it to discharge. In essence, the resistor is going to put the brakes on. All right, so the capacitive time constant tells you, more or less, it tells you how fast you can actually discharge or charge up a capacitor. That's what it means. Technically speaking, the amount of time it takes for it to reach 63% of its maximum value, but that's more of a technical definition. All right, so by controlling your resistance, you can actually you get to control how fast you can charge it up, or how fast you can discharge it. So the capacitance is going to tell you how much charge you can put in it. But here's your gas pedal, or here's your brake mechanism. All right, so by controlling the resistance value, you can definitely make it go faster or slower. All right, so when you use this equation, whenever it's charging up. All right, so this equation that you're looking at represents the charge up. All right, so this is the charge up equation, or charging equation. All right, so in the denominator of the exponent, you have tau, the capacitive time constant. Okay, speaking of this being a capacitive time constant, okay, eventually we will have an inductive time constant. So it sometimes helps to put a C at the bottom. All right, so that is your capacitive time constant. The time it takes for it to charge up, or how fast it's going to charge up. The second